So the two sections are intro to probability, which is obviously what I'm going to do first, and then we'll then move on to complex probabilities, more difficult probabilities if you prefer. So I'll keep that out of the way for a minute. Here it is. What is a probability? Well, you know, I don't know what you know. I would strongly suspect that everybody has some idea of probability. It's not an unknown term you'll have picked up somewhere or other. Basically, what is a probability? Well, it's a number just getting someone in. It's a number that tells you is that enough W? How likely an event is to happen. So what we're trying to do here is we're trying to put a number on an event happening. And we have to do it in such a way that it is useful and that it's standardized across the world. So everybody talks about probabilities are talking about the same thing. Now, the generic version, right, the very simplest version of a probability would be something like this. The probability that event A happens. Except we won't write it that way because that's too much English. And we can imagine someone in France having problems with some words that aren't French. You will find that it's almost always abbreviated to that. So if you ever see a capital P brackets A, you're really talking about the probability that event A happens. Now, what's the definition of that? How do you calculate it? Well, you find a number of ways A can happen. Now, since we're using English, I can get away with that. And you divide it by the total number of possible events. Right, let's put that into context. Take a simple example of you rolling a dice. If someone said to you, what's the probability that you roll a dice and you get the number 3? Well, it's made up of two numbers, right? Basically, it's going to be a fraction. On the top is, how many ways can you get a 3 when you roll a normal dice? And the answer is there's only 1 3, so they're one of them. And the bottom number is how many possible things could happen. When you roll a dice, isn't there 6 possible things that could happen? So the probability that you roll a dice and a 3 happens is 1/6. Now there are 3 different ways to write 1/6. You can write it as a fraction, and some of your answers, that's what you're going to get. You can then do it as a decimal. So I'm just doing 1 divided by 6, and I'm going to get 0.17, roughly. I rounded it off a little bit. Or you can give the answer as a percentage. So it depends on the question, which version of the answer they're looking for. So if it says give the answer as a fraction, they want 1/6. If they say give it as a decimal to 2, 3, 4 decimal places, they want that. I don't think there's any questions that ask you to give it as a percentage. But if there was, you'd write it like this. But there are questions where the probabilities are given as percentages, even although your answer won't be written that way. So far, so good. Pretty straightforward idea. These are simple one-event probabilities where you can calculate relatively quickly, almost in your head, what the thing's going to happen. So which of all the combinations am I going to do? I'm going to do all my answers to decimal places for the most part. And the reason I want to do that is, can you imagine that I had 2 different events? And if you left them as fractions, let's just pretend that they were these. If I said to you, which one of these events is most likely, is more likely than the other? That's another way of saying which of these two is the biggest, right? Do you know when they're written like fractions like that, isn't it very hard to tell which one's bigger than the other? Now, you might be able to look and see there, that's bigger, or this is bigger. But if you convert things into decimals, so 5/17, for instance, to 2 decimal places is 0.29, and 16/15, 16/52, I should say, is 0.31. Now, I don't know if that was a surprise to you or not, but this fraction is bigger than that. And it's not because the top number's bigger. That doesn't really make much difference. Don't you need to take account of both numbers when you're talking about how big something is? You know, 2/3 is really big. 22 millionths is really small, right? So you got to take into account top and bottom. Any questions so far? Seem pretty straightforward. Right, there's a lot of intro going to happen today, a lot of terminology going to appear and so on. Let's look at the range of values for probabilities. Now I'm going to draw a little number line. Oh God, that's not much of a number line. But probabilities, when you write them as decimals, and that's what I'm talking about here, probabilities written as decimals, there is a range of values. Every probability in the universe lies between two distinct numbers. And if you think about the way that it's created, which is this thing up here, what would be the probability, right, the number, for an event that could never happen? There's no chance of it happening. What number do you think that event has as a probability?
0 out of whatever the pool size is.
Right. So the lower range of all probabilities is 0. And that is events that are just never going to happen. Like the probability that a politician is not going to lie is 0, right? The probability that I'm a good singer is 0. Trust me, I know. Anything that can't harm, right, would be 0, right? Now, over at the extreme, now remember we're talking decimals here, so you have to be careful. This is 0. What's the biggest probability that you could ever get as a number?
Pool size out of pool size.
Which is another way of saying 1. Agreed? If there's only 10 things that can happen, and you're looking for an event that is all 10 things, isn't it? Full size, as you called it, 10 over 10, isn't that 1? And that is an event that will always happen. Now, every other probability in the world, if you're doing it by decimals at least, right in the middle, there's a thing with a probability of 0.5. We sometimes have English phrases. Have you ever heard the phrase 50-50? You know, that's a 50-50 bet. You know, there's a 50-50 chance tomorrow it's going to rain. What's the other terms? You ever heard the term evens? Might be a British term, right? There's an even chance of that happening. What they're really talking about is probably 0.5, right? Halfway. There's half the time it's going to happen, half the time it doesn't, right? Now, as you go up the scale on this side, don't you get more and more likely events? So if something has a probability of 0.9, another way of saying that is that there's a 90% chance of it happening, or 9 out of 10 times that event will happen. So you imagine you throw a dice or it rains or whatever it is, that's the event. How many times does you get it right and how many times you get it wrong? And if you go down this side, you end up with less likely. So something like 0.1 is what, a 1 in 10 chance of happening. So if they say tomorrow the probability that it rains is 0.1, isn't that a good chance that it won't rain, right? It could happen, right? In fact, won't it happen about 1 in 10 times, roughly? That's what 0.1 is, a tenth. So we've got this kind of spectrum. So suppose I tell you I have some probabilities. I'll call them A, B, and C. Oh, I'll put a D in. Three of these are impossible. Which three are never possible? You can't get a probability equal to what they say.
You can't have a 200% chance of something happening.
Right? You can't have a 17/11 happening. Basically, isn't that saying there's 11 things that could happen, but you managed to find 17 ways of doing it? I mean, it doesn't make sense. And isn't 1.2? These all fail because they're greater than 1, right? This one's okay, isn't it? And the reason it's okay is, isn't this a number between 0 and 1? Suppose I stick a negative in front of it. Is it okay now? No. This one fails because it's now less than 0. In fact, there's one of the homework questions where they give you a number of probabilities and you're meant to say which ones make it and which ones don't and why they don't make it for those who don't. Are we good? Right. So how about looking at two particular kinds of probabilities? First kind we're going to look at is theoretical probabilities. And the second one we're going to have a look at is empirical probabilities. Right, we'll look at the first one. You can make predictions on the probability of an event by just using logic and the idea that there's only so many things that can happen compared to the total number. So when I said to you, what's the probability that you roll a dice and you get an even number? That's an example of a theoretical probability, because we don't need to roll the dice to figure that out. We'd agree in a normal dice there are 6 possible numbers, and 3 of those numbers are even. So the answer as a fraction is a half, but I'm turning it into 0.5. That is an example of a theoretical probability. Okay, next one. Let's figure out the probability of choosing one letter from the alphabet and you happen to choose a vowel. So there are 2 numbers we need, right? The number on the bottom is how many letters of the alphabet, so we'll take it that we're using ours, 26. Please don't argue about this. How many vowels are there? Agreed? Right. I think Americans have a funny, maybe I get picked up or a student was just having me on. But do some of you think Y is a vowel?
It is occasionally. That's the English language for you.
Yeah, it goes A, E, I, O, U, and sometimes Y.
This is an American problem, isn't it?
Yeah, probably.
Good. I'm totally ignoring it. There are only 5 vowels and I'm leaving it at 5, and that makes this question more, we all agree on the answer now once I've decided to do an executive decision. Okay, they like card games in probabilities. So is everybody familiar with a 52 deck of cards, right? Forget the jokers, they don't count. You all comfortable with that? Right, so let's find out what the probability of a red card is. There are 52 cards you can choose from. How many of those 52 cards are red?
$26.
Yeah. There are 13 hearts and 13 diamonds, and they add up to 26 red. And that guy comes out as one of my very common answers, 0.5. Can you see in every single one of these questions, I didn't actually do an experiment. I didn't get a pack of cards and give them a shuffle and said, oh, that one's red, and then shuffled again, and that one's red, and oh, it's a black one, that one, and I keep doing it lots and lots of times until I guess eventually I came up with my guesstimate of that. That's what makes it a theoretical probability. You make some assumptions like you know exactly how many things could happen when you roll a dice, and you know exactly how many of them are, in this case, even. You put those together, you've got your probability. Now let's look at a different situation. Oh, let's do something with colours. So you collected some data on 50 students, and you asked them what their favourite colours were, and you got this table. Now, if we make the assumption that this sample of, what was it, 50 students, was a fair representation of everybody in America, I know this is a very simplistic question, but everybody in America, then we could make a guess at what's the probability that you choose a person at random in America and red was their favourite colour. Well, we're going to get a thing called the relative frequency. Can you remember how to do the relative frequency? 5 out of 50. Isn't that very like how you calculate probabilities? 5 out of a total of 50. That ends up being 0.1. This information was not done by theoretical, probability techniques. Wasn't this done by using a table of values? Couldn't someone else ask another 50 students and get a slightly different answer? In fact, I would be amazed if you got the same answer. What would happen if you asked 500 people? Do you think that the proportions would stay the same, or do you think they might wiggle a little bit? If you asked 500 people that same question and you only gave them 3 colours, do you think you'd get 50, 150, 300? Do you think it would come out exactly like that just because you're now asking 500? Or do you think there'd be differences?
It's going to be different because those are constants.
Right? 500 people is not the same as 50 people, right? So the thing about empirical probability is that number is our best estimate of what the American probability of that event happening, right? It's like me saying, Chloe, what's your favorite color? And she's saying red. That's only going to happen 0.1 of the time, right? If I choose someone at random. But it is only an estimate. If you use 5,000 people, you get a different estimate if you use 5 million. And so we come up with an interesting law. It's called the law of large numbers. That's its name. I like its name because it kind of is giving a clue what's going to happen here. It says, if you choose a really large, this is my phrasing, sample size, the relative frequency will become very close to the real probability. So if I asked 500,000 Americans the same question, they could only pick from these three. Would you agree that that 500,000 sample would probably give me a really accurate answer on what's the probability that people like red in America?
Yes.
So it's really just a relative frequency, but that's what a probability in these contexts are. So that's what empirical looks like. It's a table of values where you know numbers, right? And theoretical, you don't have a table of values. You can calculate it basically just by using an understanding of what numbers belong in top and bottom. Are we good? Now, told you today's, at this beginning of today, has got a lot of stuff going on. So here's another thing. It's called the complement of an event. Suppose A is the event, it rains tomorrow. The complement of A with a little funny C above it is the notation they use, is the opposite event to whatever A is. So if A, it rains tomorrow, what would the complement of A event be? Well,
It doesn't rain.
it doesn't. And very often sticking the word doesn't in kind of does it. It gives you an idea what it is, right? So it doesn't rain, which I could abbreviate to say dry, right? But it doesn't rain is a good way to phrase it.
Go to the gym.
It doesn't rain, right? Rain. How can I use that? Well, suppose you get a really, really good baseball player, and the probability that when you throw him the ball, and it's not a foul ball, right? A ball he gets to hit, right? The probability that he hits a home run is 0.4. That guy would probably be worth a lot of money if he had that number, right? Well, we'll call that A, right? Then the probability of A thing is the probability that he doesn't hit a home run. We can actually calculate what that answer is. If you have a 0.4 chance of getting it, you always have a 0.6 chance of not getting it. Well, think about that. If there's a 30% chance it's going to rain tomorrow, isn't there a 70% chance it will not rain tomorrow? If I've got a 1 in 3 chance of remembering my name tomorrow, then there's a 2 out of 3 chance I won't remember my name tomorrow. It's written as a little funny formula, and it basically says this. The probability of an event plus the probability of the complement of that event, which is what this cell is, always adds up to 1. Now, imagine I have a little empirical table. And there's only 4 things that can happen. And I tell you this is point 1, this is point 2, this is point 3, and this is point 1. Ah, okay, I'll have to change my question. I overshot it. Do you know I can find out what the last answer is, even although there's no other information there? If there's only 5 events, and these are the individual probabilities, what's the probability of the missing event?
0.3.
You want to tell, you're right, how you came up with that number, that decimal.
I added them all together and subtracted them from 1.
It's as simple as that, right? Don't overthink the early stuff, right? Are we good? So, if you know the probability of an event, don't you also know if you know the probability of an event, don't you also know the probability of its complement, the thing not happening? If you know a table, even if it is, in this case here, it's an empirical data table, can't you leave out one answer and you'll still be able to figure out the others? Okay. Now, let's look at a thing called sample space. I'll say SS for short. It's a list of all possible events. So the sample space is a list of all possible events. That can sometimes catch people out. I'll give you an example. Suppose you have a family of 3 children. And we'll make an assumption just to keep things easy, that it's just as easy to have a boy as it is to have a girl, right? So they're equally likely events. If I asked you, what's the probability that you get 3 girls? So you've decided you're going to have 3 children. What's the probability that you get 3 girls? Now, the typical way of doing that, and it's still correct in this question, is you find out a number of ways of getting 3 girls. And then on the bottom, you put the total number of possible events, right? Your sample space is going to help you answer this question. I could probably answer the top one. Would you agree there's only one way of getting 3 girls? A girl, then a girl, and then the third one was a girl. So in this case, I could probably do that without work. But how many, what's the number that goes in the bottom? Three children in the family. I'll tell you, it's not 3. I know 3 children, 3, it sounds right, but it isn't. It's not 4. It's 8. Now, to do that, you need to know every member of the sample space, and then you add them up. So let's show you where that's coming from. You could have 3 girls, right? And the order in which the children appear is considered important. So getting a girl, then the next child was a girl, and then your third child is a girl. That's how I'm going to read this. Couldn't you get a girl, girl, boy? A girl, boy, girl, and a boy, girl, girl. Do you see that I'm writing these down in a kind of systematic way so I don't miss any? So I started off with 3 girls. Aren't the next 3 situations how you can get 2 girls and a boy in different ways? Right? Now, what do you think I'm going to do for the next 3?
Boy, boy, boy.
Oh, I certainly could do that, but I'm going to put that down here. What should I do next? 3 girls, 2 girls and a boy. What do you think I'm going for next?
Boy, boy, girl.
Okay, let's do that. 2 boys and a girl. A boy, girl, boy. And finally a girl, boy, boy. Now you add them up. There's 8. Which means that this number is 8. Because there's 8 different combinations of 3 children in the family when the order in which the children appear is important, which we always consider it is. Does that make sense? This here is called your sample space. Now, suppose I asked you, what's the probability that you get more girls than boys? Well, we know the bottom number is 8. So we're looking for families where there's more girls in the family than there's boys. So would you agree that 3 girls count? There are definitely more girls than boys. Would you agree that one, and that one counts? So the probability that you have a family of 3 children and you have more girls than boys is 0.5. Roughly half the time that happens. So I don't know if you know any families of 3 children, but half of those that you know, if you know more than a few, half of those will have more girls than boys. Do you know the other half will have more boys than girls? Is it kind of symmetry to that answer, isn't there? True story. One of my sisters, my sister Morag, wanted girl, desperately wanted a girl in her family, and she got 4 boys. Boy, 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 boy. Right? And she gave up. That was it. And every single one of her boys has their own family now. And every single one of them, their first child was a girl. So go figure. What's that phrase? You can't win for losing. So genetics is a weird thing. Yeah. There are some families who just seem to have, tons of girls in them, and other families that don't. Right, are we comfortable with the sample space idea here? Right. Not all sample spaces should be written down. If I talked about what's the probability that you get a heart when you play a deck of cards, do you think you really need to write down all 52 cards to do that kind of question? Would you agree in this case here, it probably was at least helpful the first time to write down the 8 things that could happen in your sample space? And then you can do all sorts of questions using that. What's the chances that it's a girl and 2 boys? What's the chances that it's more boys than girls? What's the chance it's 3 boys? Anything you want, you can now pick and choose from here. Oh, here's a side question. Dot, dot, dot. There are 8 things in that sample space. It's important that you know how many there are so you can stop looking. So here's a way to find out. The first child, the second child, and the third child. Aren't there 2 different choices? The first child could be boy or girl. Aren't there 2 choices for the second child? It could be a boy or a girl. And aren't there 2 choices for the third child? If you go 2 times 2 times 2, do you see that you get the 8 that is in the sample space? We're not going to write the sample space down for this one. But let's try and figure out how many people would be, how many things would be in that. If you've got 4 children, right, a family of 4 children, what's the combinations you could, how many combinations could you get, different ways of getting it? 4 children.
16.
2 times 2 times 2 times 2. Agreed? 16. We're comfortable with sample space. Right, here's a really big sample space. I feel like one of those people in a cooking show. Here is one I prepared earlier. When you roll 2 dice, right? See if you get 2 dice and you roll them like in craps, right? You roll the 2 dice and you add them together. That's a very common thing to do. You've probably played some games like Monopoly, right? You roll it and you get a 3 and a 4, so that makes 7. You move 7 along the board. Very common to do that. There are 36 things, here every single one of them written down. 36 things that can happen when you roll 2 dice. This whole table is my sample space. So obviously, if I'm going to do any questions with dice, and in the homework you'll find that there are dice questions like this, you kind of need this table. Either print out a version of it. You know, find, there's a ton online, you can go and say, you know, dice table or something and print one out. But whatever it is, get one. I've deliberately color coded them just to show you that 1, 2 is different from 2, 1. It's a bit like boy gets you girl, then girl gets you boy. Do you notice that we counted them as separate things? Right? A boy, then a girl is not counted the same as a girl, then a boy. They're 2 separate events. Right, now when you look at this dice, we can then answer questions like, what's the probability that you roll 2 dice and you get a total of 11? Well, there are 36 things. You can count them if you like, but there are 36 things there. How many of them add up to 11? That one? Plus that one. 2 out of 36. And if they want the answer as a fraction, because sometimes the homework does, then you simplify it down to 118. I'm going to turn that into a decimal. And it's about 0.06. So if you roll 2 dice, you know about 6% of the time it's going to be an 11. Going to do these 2 probabilities in a few seconds. Before I do, try not to look at the table too much because that'll cheat. When you think of what dice add up to, right? Isn't the smallest total 2 and the biggest total is what, 12? Right? Which one of these 2 is more likely to harm? You roll the dice and you get a 6, or you roll the 2 dice and they add up to 7? Which of those in your gut feeling do you think's the bigger? Or maybe they're equal. I guess that's another possibility. Total of a 6, total of a 7. Right, Daniel, I'm putting you on the spot. Give me a vote. 6 or 7?
6.
Okay. Stacey, give me a vote. 6 or 7?
6.
Olivia, 6 or 7? You try to calculate it. Come on. What you got? 6 or 7, Olivia? Which do you think? Olivia Hall.
Oh, sorry, spacebar's not working. 6.
6. Okay, every single one of them said 6. Let's find out. How many ways can you get a 6? Well, I'll put my pen on it. Well, that's probably a bad choice. 1, 2, 3, 4, 5. We agree that there's 5 ways to get a total of 6. 1, 2, 3, 4, 5. So 5 out of 36. Let's look at getting a total of 7. 1, 2, 3, 4, 5, 6. Do you see how your intuition can throw you? It's not uncommon that people think that a 6 is more likely, and there are a lot of sensible reasons why you would think that. Your brain might be thinking, look, half of 6 is 3, half of the other 6 is 3, stick 2 3s together, 10, 6 sounds like a reasonable total, right? That kind of logic. Do you see how it fell apart when you actually calculate it? Now, probability has a very disreputable background. A lot of math came from the airy-fairy stuff, right? Ivory towers. But probability came from gamblers going to mathematicians and saying, I'm playing this new game where you throw 2 dice and it depends on what the total is. If you pick the right total, you win. I need an edge. Can you come up with some way of deciding what would be a good gambling strategy? Which one should I bet on more than any other? Well, can you imagine you're just simply betting on a game for what total appears? Forget craps, which is much more complicated. But there was other games. There was a simple game where you rolled the 2 dice and you put your money in the total. And if that total came up, you got more than just your money back, right? You won something. And if anything else happened, right, they took it away and the casino would keep it. Can you imagine in this case then, that guy would say, bet a total of 7. It's not guaranteeing you're going to win, but it does at least improve your odds. You probably haven't done this, but I like probabilities and things like that. Have you ever watched a poker game on television, like the World Championship of Poker? You might watch it for 5 minutes and you get really bored because it's hard to watch that kind of sport, if you call it sport. Do you know when they're looking at the hands, they have things like, this guy's got 2 kings and some other cards, and this other guy's got an ace jack. And then they tell you the chances that that person's going to win, even before they flipped over the last of the cards. Those kind of things? Do you know that's all done through probability? And if you're a good poker player and you want to win, you really do need to have a fundamental idea of how likely certain cards are going to appear given what you've got in your hand, for instance, right? And equally, I guess, what's the chances that my opponent might end up with some cards that are going to beat my hand? And so there's a lot of very good intuitive probability people in the poker world. I really think that's a big skill, to being able to judge that. So are we comfortable with this kind of guy? Big long table, lots of cool stuff. Right, let me go into the homework then, and we will show you our first group of questions. I think I set it up right. Hey, we're on a roll. Okay, right, a quick video, you can do that on your own. Right. Okay, here's our first question. Suppose a newspaper states that the probability of rain today is 70%. What is the complement of the event rain today? And don't overthink
No rain.
it. No rain. Here are 2 very simple probabilities, so these again shouldn't take us very long. What's the probability of an event that is certain to occur? We've already talked about that today.
1.
Correct. And what's the probability of an event that's impossible?
0.
0. I've already talked about the law of large numbers, so I'm just going to zoom by that guy. And I've just realized we got the answers here, and that's a big distraction to me. Okay, here we go. Why are your answers still there? Go away. Now, I'm not going to go into the specifics here, but just basically how you would do this. A recent survey of 1,030 American adults selected at random, 641 considered an occupation like firefighting to have very great prestige. Yeah, I'd probably be one of those. Estimate the probability to the nearest 100 that any US adult will think the same thing. Now, this, although it's not stated, is an empirical probability. Because haven't you only asked 1,000 people and you're going to use that as your estimate? But won't your estimate to the probability simply just be 641 divided by that guy? Does that make sense? 641 divided by 1,000, and then you write down your answer in here, and I'm pretty sure, yeah, to 2 decimal places. Now, this one's a cool question. I like this a lot. Do you notice that what you've got here are various combinations of males and females that you could get from a family of 4, right? Let's just count them for a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. There are 16. That means they're all there. Okay. Now, they're talking about the assumption that they're all equal, which is fine. List the equally likely events for a gender of 4 children, from oldest to youngest, male and so equally likely events. There are many different answers. It depends on who you pick first. I'm going to pick, at random, 3 females and a male, right? Now, they say equally likely events. So I could say another 3 females and a male, but maybe in a different order. I could say that one. I could say that one, right? And that would be correct. But here's something that might surprise you. Isn't that event also just as likely? Isn't getting 4 females or 4 males or a female, male, female, female, isn't every single one of those 16 things equally likely? So the answer is, in fact,
Those ones mess me up.
right? Does it make sense the way the
Yeah.
question was phrased? Right. Now, if the question had said, choose the events that represent 3 males and 1 female, right, for instance, wouldn't you go through it and only pick the ones that that was true for? If they'd said, list the events where they're all the same sex, wouldn't you just tick the female, 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 or the 4 male one, right? In this case, equally likely. Now, I've already mentioned this question, so I'm only going to choose one of them. Question C. Explain why 120% can't be a probability. And you can only pick from the 3 choices below it.
Because it's got to be between 0 and 1.
End of story. I did this with my other class and I got really disappointing results. It's not their fault. I just asked them, can anybody here wiggle their ears? And only one of them said he could. Does anybody in that? Who said that?
I can barely do it.
Barely is better than most people. I can't even. If I try to wiggle my ears, I try and think of a muscle that's over there. And as far as I know, I don't have anything over there to wiggle them with. So I don't even know how to tell my brain to wiggle my ears. It's a weird thing. But evidently, Chloe can at least do it partially. Thanks for sharing. So roughly 1 out of 30, unless someone else in this class can wiggle their ears.
Yeah, I can. I didn't know that people couldn't.
If I put you in the spot, could you wiggle them for the rest of us?
I guess. I mean, I don't know. Can you see?
Well, I'm going to put it on a slightly, I'm going to close this for a minute. This has nothing to do with what we're doing, by the way, you all know that. It's just that I want to do.
Okay.
Right. Wait a minute. If I can make you go on full screens. Yeah. Wiggle your ears. Gosh, she's
Can you tell?
wiggling them. I see it.
Yeah.
It looks to me like you're using something to do with your jaws.
Yeah, it's a jaw muscle. Yeah, because it wraps around towards the back of your head. It's that same muscle that controls your jaw.
No, I still can't make mine wiggle. It's evidently a what's the word I'm looking for? It's a skill that I don't have. Now, anyway, if you read the story, it ends up being 13% of their friends can wiggle their ears. And the result then is that a guarantee that the Americans, 13% of them can wiggle? Not really, isn't this is an empirical phenomena? It's based on a small sample of our friends. You can't say for sure that that's the entire American continent, but at least it's an estimate. Right, let's look at question 9 then. This person was a pioneer in the study of personality types. The personality types are broadly defined according to 4 main preferences. Oh, this is interesting. Didn't read the last part when I checked this. Do married couples choose similar or different personality types as their mates? Right, so if you're both extrovert, did they mention what the things are? No. I'm making a guess. Extrovert's one of them, right? Introvert would be a second one. I don't know what the other groups are. But, you know, the introverts marry introverts or the extroverts marry introverts. You know, that kind of combination thing. Yeah. Number of similar preferences, 4, 3, 2, 1, or none. Okay. Use this data to estimate the probability that they will have 0, 1, 2, 3, or 4 personality preferences in common. An answer to do decimal places. Okay. If you wanted to do 0, wouldn't that correspond to the 40 people? 40 out of 375. So I'll just do that one. If you go to your calculator and you go 40 divided by 375, I get roughly 0.11 to 2 decimal places. It looks to me, yeah, okay. This is my interpretation of that data. I'm going to put 3 in right now. 124 divided by 375. That's about 33%. So you can imagine turning the rest into what they would be, right? Just basically relative frequency. 40 out of 375, 64 out of 375. Now I'm just going to look at this raw data. And what that is telling me is that we like people to have at least something in common. But we don't like it when you have too much in common, because there's 27. And we don't like it when we have nothing in common. So it's not a, you know, we like people who are identical to ourselves. I think it probably means we like people whose personalities are very similar to ourselves, at least according to this data. And I am not one of those because I talk too much and my wife hardly talks at all. So there's a definite personality trait that we don't share. I love really bad jokes and my wife doesn't. There's another personality. But I do love my wife to death. I'm really happy I married her. We do share some things in common. We love travel and we love family. And she is extremely honest. I've never met anyone quite as honest. Tell you how honest my wife is, to give you a story. We went into a supermarket one day, and you know sometimes at the bottom of the cart, you don't even know you've done it until you've left the building. There was an item that we never paid for. And my wife always goes back and buys it.
Oh,
That's how honest my wife is, right? I mean, I do as well, but my wife is an amazing person. So, I mean, that's probably the pluses, right? And the fact that she doesn't like my jokes. You can't really hold that against her, can you? You've heard some of them. right? So you can't really hold that against her. Now, it says here, and this is a technical issue, do you know these 4 probabilities should add up to 1, but they don't always add up to 1? And the question doesn't put it in that phrase, that phraseology. I wish they would. Do you notice that I'm rounding off to 2 decimal places here? Couldn't there be a situation where the answer ends up being 1.02? Can you imagine you added you calculated 4 decimals and they all rounded up and 1 decimal rounded down? Wouldn't the total be a little bit bigger than 1 because of that? So it's not that the total shouldn't add up to 1, the total should. And if you did them to 2 million decimal places, they probably would. But can you see that when sometimes if you round off decimals, you can introduce a little bit of error? So when you're doing a question and you do the check, and the check is always add them all up and see if it equals 1, will you be a little bit generous with yourself? If you add them all up and it equals 0.99, will you say I'm right? There was some rounding off things that caused that little discrepancy. Now, if you add them all up and it comes to 0.75, you're wrong, right? If you add all the probabilities together and it's 0.75, you are wrong. If you add them all together and it ends up being 1.2, you are wrong, right? Because shouldn't the answer be 1 or darn close to 1 bar rounding off errors? And that would have been a better phraseology. And I've got some sample space things. And here's a dice one. I think that's pretty straightforward. And okay, here is some data where they collected, who is that, US Today, found a survey of 966 inventors. So I'm assuming these are people that work for research and development. You know, big companies have departments whose job is to think up clever things to make or improve on, right? The R&D department. So those are probably the inventors. So they may even be people who invented something and built their business around it, right? Anyway, 966 of them. And they went and asked them, at what time of day do you get your best ideas? And they broke the day into roughly 4 equal parts, you see it? And for instance, 305 out of that total of 966, that 305 out of 966, their best ideas occurred early in the morning, right? In fact, that number there is quite interesting. Do you know that most of these people didn't get their good ideas while they were at work during work hours? To me, work hours are very, very roughly 12 to 6, right? You got your best ideas once you were sitting at home watching TV, eating your dinner, and then an idea, oh, maybe if I did that and this, it would improve the, you know, the gizmo. So your best ideas, according to this data, don't typically occur when you're at work. Now, if you're in charge of a big company like Ford, do you know what Ford should say to people? Don't bother coming into the office. You're not going to have any good ideas today. Just go home, and when you've got a good one, come in. You know, just change their day around. A bit like teleworking, right? You're shaking your head like that ain't going to happen. Olivia, it was your head I was looking at.
That's just the dream. I would love to do it. Granted, I haven't worked since the end of March, so I have no room to talk here, but man, that sounds good.
What, that just don't come to work until you've got a good idea?
Sounds good to me. I don't have any ideas at all. Call me next year.
Well, there'll probably be a proviso. And if you don't have one within a month, you're sacked. You know, just to give you some motivation.
That's fine. I'll work for Chevy. That's all right.
Okay. I'm just going to pick one of these. See that 335? It goes in here. And when you do 335 divided by, what would that number be? 966. And could you imagine turning that into a decimal and put your answer in there to 3 decimal places? Now, by the way, let me do that one just because it's there. So I'm going to do 335 divided by the total of 966. And the the guy I've got here is this fella here. And it's going to be wrong because I'm deliberately doing it wrong. What did I do wrong? Because it might look quite like, you know, you might be doing it in your calculator and saying, yeah, that's kind of what I got rounded off. What's wrong about that answer?
This question wants it to 3 decimal places and not 2.
That's, and someone was talking earlier about sometimes, can't the homework be pernickety? Don't know if you know that word, right? Fussy. And so you could easily just miss that 3 decimal places. Why? Because the last 4 questions were all 2 decimal places, right? And you're in a 2 decimal place, you know, zone. You think everybody's 2 and you don't bother reading carefully enough. So simple things like that can cut you out. Oh, I can answer this one quick. What is the sample space for this problem?
The entire day.
Yeah, broken into 4 pieces, but it's still the entire day. And here's something to do with germinating, and here's something to do with computers. And I'll leave that one because it's a little bit trickier. Right. So we have got to our first break for today. So I'm going to give you 5 minutes to get a coffee, to practice wiggling your ears. Olivia is giving free lessons. And it'll give me a
How
chance
about
to...
3?
Oh, that's right. She's not been working since March. She probably needs some finances. Right. So if you want to, you can do that. But I'm just going to chill out for a few moments myself. It gives me a chance to get ready for our next section. As I say, you know, do whatever you're doing, and I'll see you back here. Okay, looks like it's about time. Okay, hi everyone, we're back. And we're going to look at the next section, the last part of chapter 4. It's a bit longer than the first one. We're going to look at how to calculate complex probabilities. And again, there's going to be quite a lot of different terms that are going to get used and some formulas as well. So, which one shall I start with? Let's look at what's called independent events. Okay, independent events such as A and B. So, two events, A and B.
Can you turn the camera on? We can't see it.
Well caught, thank you. Right, so independent events. Two events, A and B, are said to be independent. If the probability of A happening has no effect on the probability of B happening. So if the two things are independent, the two events have no effect. They do not interact in any way. They do not change the probability of those events happening. Example. Suppose A is you throw a coin and you get a head. And B, you throw a dice and you get 5. Would you agree that if I did both those things, so I get a coin and I throw it in the air, and at the same time, on my other hand, I roll a dice, that if the A event was a head, does that affect the chances that the dice is going to be a 5 or not a 5? Does it have any interaction with the second event, either physically or probability-wise? The answer is no. Those two events are completely independent of each other. Right? Now, when two events are independent of each other, the probability that A and B happens is the same thing as the probability of A times the probability of B. So in this case, what's the probability that you throw a coin and get a head is a half. And what's the probability that you throw a dice and you get a 5 is 6. And that ends up being 1/12. And as a decimal, 1 divided by 12 comes out as about 0.08. This here is sometimes called the probability test for independence. So you find the probability that A and B happen, and then you find these two individual probabilities, and when you multiply these together, if it's the same as that, then they are considered to be independent events. They don't affect each other. Now we're going to look at a term called conditional probability. And it has a look that looks like this. And It's designed to be international. Can you see that in the way I've written this? It doesn't matter if you're German, Chinese, French, Scottish. It just has symbols, right? And you can all use your own language for what those symbols mean. I don't know what the French for probability is. It's probably some word that sounds very similar to probability, right? But it doesn't really matter. So the way you read this is it's a probability that event A happens. That vertical line is, in our language, for the word given. And this fella here, that B has already happened. So we call these types of probabilities conditional probabilities. So you're not just finding the probability of A, you're finding the probability of A given another piece of information. Sometimes that information can make the probability more likely, sometimes that information can make the probability less likely. And sometimes it has no effect at all on the probability. So let's do this. What's the probability in a normal deck of cards you get a king? Right. Well, there are 52 cards in a deck, right? 4 of which are kings. And that ends up being 1 divided by 13. And that ends up being roughly 0.08. Now, what's the probability that you get a king given that it was a red card? So you're not told the entire thing. It's a bit like somebody was cheating. I can't quite see what card you've got, but I did get a glimpse of it and I knew it was red, right? Now, how would that work out? Well, since you now know it's red, doesn't that mean that there are only 26 cards it could be? There are only 26 red cards in a deck of cards. How many of those red cards are kings? 2. And, although the numbers came from different places, don't they end up at the same answer? What that tells me is, do you know that kings and being told that it was red had no effect on the probability? Wasn't the probability of getting a king still 0.08? Now, side issue before I do the next one. A face card. A face card is a jack, a queen, or a king. And they're called face cards because there are little faces on them, right? The queen's got a little face of a woman, the king's got, a guy, and the jack's a guy, right? So a face card is a jack, a queen, or a king. Let's do that probability, that conditional probability. What's the probability that you get a king given that it was a face card? How many face cards are there in a deck of cards? So I've been told, I got a glimpse of it. I know it's a face card. Can't tell you anything else because I can't see anymore. But I knew it was a face card. I could tell that much. What is a face card? How many are there in a deck?
12.
Great. 4 jacks, 4 queens, 4 kings. 12. Of those 12 face cards, how many are kings?
4.
Do you see, in this case, your probability is much higher. If I know that it's a face card, if I cheated in some way and found out that it was a face card, is it my chances of getting a king much better than they would be if I knew it was a red card, or if I knew nothing at all? In fact, knowing it's a red card and knowing nothing at all are equivalent, right? Because you're no better off. What's the probability that you get a king given that it was not a face card? Well, there's an awful lot of cards that are not face cards. Can you trust me? There's 40 of them because there's 12 that are and the other 40 are not. How many of the cards that are not a face card are kings?
4.
In fact, is there any? It's a bit like a trick question. Are there any kings that are not face cards?
No, there are not.
So the answer in this case is 0. Can you see how a conditional probability can have no effect on the original, can make it much more likely than the original, or make it much less likely? In this case 0, but it could be less, right? So conditional probabilities are very helpful because they allow us to adapt or alter a probability based on given information. Now I'm going to put conditional probabilities together and show you an example of another complicated probability. Here's the story. We're going to take 2 cards from a deck. And it's called without replacement. In other words, once the card is out, it's used up. Now I'm going to calculate what's the probability that I get dealt 2 kings. So I'm just going to call it king, king, right? 2 kings. Let's see how that would work. Okay, I'll call that the first card. I'll call that the second card, right? So what's that going to be? It's going to start off with, what's the probability, pardon me, that I get a king, right? So I've got my 52. I turn over the first card and, way, it's a king. What's the probability of that happening? 4 out of 52 cards, right? Now it gets a little bit more awkward. What's the probability that the second card is a king, given that the first card was a king? Because isn't that the only way I'm going to get a pair of kings? The first card has to be a king as well, right? Now the world has changed here. This has happened, right? It was a king. Aren't there only 51 cards left in the deck now? Because one of them's been used up. It's already down on the deck, right? Here it is here. There's my king. How many kings are left?
Only going to be 3.
And so you multiply those probabilities together, but do you notice in this case the probabilities have changed because of the conditional effect? So you put those together, and I'm just going to do it on the calculator. So you go 4 divided by 52 and you get that ugly guy, then you multiply it by 3 and you get that guy, and then you divide by 51 and you get that guy, and I'm going to have to go 0.005. Can you see how hard it is to be dealt a pair of kings? So if you're playing blackjack and you get a pair of kings, you should feel fortunate, shouldn't you? Because it's not going to happen that often. How about this one? What's the probability that you get 2 red cards? Do you think that's going to happen pretty often? 2 red cards. Pretty common? Okay, what's the probability that the first card is a red card? Well, there are 26 red cards out of 52. That's the easy one. What's the probability that the second card is a red card, given that the first one was a red card? Well, things have now changed again. Isn't there only 51 cards and there's only 25 red ones? Do you see how that goes down by 1, this goes down by 1? Now, that's still a pretty decent number. It's not huge, but it's pretty decent. And the answer I get is about 0.25. So do you see how conditional probabilities are going to be a little bit more complicated? They have to be done in a certain order. Now, there are some formulas that I'm now going to write down and that we are going to use. The minute I find my little sheet, here we go. And these are telling us that you can find the probability that A and B happens by doing this and by doing this. These two guys here are actually what I just did a few minutes ago. You know, you do the guy, then you do the conditional guy. They've just put the order a little bit different in this case. This fella here is quite interesting, because you can now calculate a conditional probability by using this formula here. So let's use this formula. Suppose I tell you the probability that A and B happening is 0.7. And I tell you that the probability of B happening on its own is 0.9. Then I should be able to calculate the probability of A given B, because I'll use this formula here. And it says it's A and B divided by the probability of B. And this is 0.7 divided by 0.9. And 0.7 divided by 0.9, it's about 0.78. So if you give me any two out of the three, I can find the third one. So if you tell me this guy and this guy, can't I find that guy? Right. If you tell me these two, can't I find that guy? So the interaction between an A and B, right, that's like the first and the second both happening, right, is the same as this conditional probability times A. In this case, I'm saying, look, I can find this if you tell me these two. So let me see if I can do a different combination. Suppose I tell you that the probability of A given B is 0.6. And I tell you the probability of B is 0.3. You should be able to find the probability of A and B. You can use this formula. And it's the probability of A given B, 0.6, times this guy, 0.3. And so the answer is 0.18. So these are equivalent. All these formulas are really saying the same thing in different formats. Essentially what you need to get from this is, if you can tell me any two out of the three, I'll figure out what the third one is. And that's what some of the questions in the homework do. I mean, they tell you these two and you find that, or they tell you these two and you find this one. It's always a kind of, here's two of the three, figure out the third missing one. Now, if A and B are independent, that will be true. The probability of A given B will be the same thing as just getting A. So, the probability that you get a king, given that it's a red card, wasn't that the same as just finding the probability of the king on its own? Remember we did that one earlier? Do you know that means red cards and kings are independent of each other? Now we're talking probability independence, because a lot of you are going to say, but wait a minute, red cards and kings have a connection, right? There's some red kings, for instance, right? And that's true, but that's not what independence is about. Independence is not that you don't have things in common. Independence means that the two things don't affect each other's probabilities. For instance, what's the probability that you get a red given that it's a king? And what's the probability that you get a red card? Let's do those two and see what happens. If you get a red card, isn't it 26 out of 52 cards? 0.5. What's the probability that you get a red card given that it's a king? Well, if I tell you it's a king, doesn't that mean there are only 4 cards? How many of those kings are red? There are 4 kings. How many are red? It's not a trick question.
It's 2 out of 4.
Yeah. And wait a minute. Isn't 2 out of 4? 0.5. Do you see being red and being a king are considered independent events? They have no effect on each other's probability. Getting the thing with that information or getting the thing without that information, don't they still end up being the same number, 0.5? So that's what independence means. It doesn't mean that they have nothing in common. It means that they don't affect each other's probabilities. That's what independence means. So we're now going to look at a second very common term. Mutually exclusive. Now, A and B are mutually exclusive. I'll just say ME. Means that they do not share any common events. So if event A is made up of 2 or 3 different things, and we call it event A, and event B is made out of 5 or 6 different things, but they don't share anything in common, they are considered mutually exclusive. And they sometimes see in books where they draw little pictures and they say this is A and this is B. Do you see they don't have any overlap? So do you know A could be face cards, right? Jack, queens and kings. B, on the other hand, could be aces and 2s. Do you see that those would be considered mutually exclusive? Face cards don't share anything common with aces and 2s, for example. Can you imagine males and females? Can you imagine, it's hard to imagine some, too late in the day for my brain. Give me 2 mutually exclusive events where you have to belong in one or the other, but you can never belong in both.
Going to work and not going to work.
Okay, working and not working, right? In fact, now that you've said that, won't A and the complement of A be always mutually exclusive? So raining, days where it rains and days where it doesn't rain, right? People who are males and people who are not males, right? That kind of dichotomy. Now, mutually exclusive is not the same as independent. Remember, we talked about independent. You could be a face card and you could be red. Aren't there some red face cards out there? Can you imagine face cards in red? But aren't they also independent? Because doesn't the probability of face cards have no effect on the probability of red? Remember the questions we did, the conditional probabilities. So how do mutually exclusive help us? Well, mutually exclusive helps us to do questions that involve ORs. Conditional probabilities use independence, and they are very often used where at least one of the things that you're looking for is A and B, right? Probabilities with the word and in them. Now we're going to look at probabilities with the word or in them. So before we go any further, there is a problem with the word or. There are two versions of the word or. There is the inclusive or, and there's the exclusive or. Did any of you know that already? Because maybe you've done some stuff. Computing very often has two versions of or, don't they? When you do truth tables, there are two versions of or. The English language tends to only use one of them, and therefore we think or means what I'm about to say, but in fact it doesn't. Statistics uses the other or. It's called the inclusive or. So in English, you would say to your kid, you can have ice cream or you can have cake. Now, when you use that word, don't you automatically mean you can't have both? Because that's why you tell your kid, ice cream after dinner or some cake after your dinner, right? And your child should know, okay, I must pick one, I can't have both. That is the exclusive or. Statistics uses the inclusive or, which means you can have ice cream, you can have cake, and you can also have both. That is included in the word or. Now, do you see how it's a little bit different from what you think or means? Because you're used to the English version of or, and you have to kind of change your mentality a little bit. If you want to visualize it, here's A, here's B. The English version of or is you can have anybody in this chunk and anybody in this chunk. But you see the piece that's the overlap, you're not allowed to eat that. You can't have both of those, right? That's the English version of or. It's actually called the exclusive, right? But what does our version look like? There's A, there's B. If you do an or, it doesn't matter where you came from. Either A or B or both, you all count. You see how you're allowed to choose now a different kind of grouping? In particular, aren't you allowed to pick people from that little overlap in the middle? So there are two calculations that are going to happen here. If they are mutually exclusive, then it's going to be just you add the two probabilities together. And if they're not mutually exclusive, but you still want to find the probability of A or B, then you get the probability of A, take away the the probability of B, take away the probability of A and B. Okay, let me show you two versions of that being used. Let's do the first kind, mutually exclusive. We'll do deck of cards. Okay, I want to know the probability that I get king or an ace. Would you agree that kings and aces are mutually exclusive? If you're a king, you can't be an ace, and if you're an ace, you cannot be a king. Great? So let's see how the or works here. Well, it's the probability of you get a king plus the probability of you get an ace. Isn't that just, in both cases, 4 out of 52? Which is what? 8 out of 52. And the answer I get out of this is 0.15. So what's the chances you get? Now, I could have done that calculation without this. Couldn't you just say 4 of these plus 4 of these gets you 8 out of 52? And that would probably be the quicker way of doing it, right? There are 4 kings, add 4 aces, that's 8 cards altogether. 8 out of 52 becomes this decimal. We are done. So mutually exclusive events can probably be added up in your head relatively easily. But what about this? King or a red? Is king and reds mutually exclusive, or do they share some terms? I see some nods, so they share terms, don't they? Now that means that calculating the probability of a king or a red gets a little bit messy. Let's pretend I do it wrongly. Let's pretend I don't pay attention to that. Oh, I know how it works. There are 4 kings out of 52. There are 26 reds out of 52. That adds up to 30 cards out of 52, and then I get my decimal, and off I go, and I'm kind of happy. But you know that's the wrong answer. Because in these 4 kings, aren't they already being included in these 26 red cards? In fact, how many kings are red? Because that's the both part. 2. So what you should have said is the kings, which is that guy, the reds, which is that guy, and then you take away the both, which is that guy. So in fact, the correct answer is only 28 out of 52, and then you get your decimal. So you see, it is important that you calculate correct probabilities, because if you're a gambler and you do not factor in things like, oh, yeah, I'm looking for a red king here, but you know, I've got to make sure that I count them properly, or I might overinflate my chances of winning and then gamble more than I should, or I might underestimate my chances of getting the cards I'm looking for, and therefore I miss a chance of winning more money, right? Because in their game, they're kind of probability, how much I'm willing to bet, right? If you get a good chance of winning, shouldn't you bet a lot of money? And if you've got very little chance of winning, shouldn't you either fold or bet a little money and hope the other guy folds, I guess, is the alternative. So knowing these probabilities is an important skill. So far, so good. Right, let's have a look at, no, we need a joke. Yeah, we need a joke. I need a joke. We need a joke. So Daniel, have you got a joke for me while I'm thinking? Because I don't have one in my head right now.
I am horrible at jokes.
That is not a joke. That is a statement of fact, perhaps, but not a joke. Okay, I got one for you. Do you know how we were talking about Australia earlier on in one of the conversations? So here's a joke about Australia. See, I like jokes about almost everywhere. This guy arrives in Australia, and when he gets there, he gets to passport control, and he hands over his passport, and the Australian, you know, guy looks at him, and customs guy, whatever you want to call him, and he looks at him and he says, "Have you got a criminal record?" And he looks back at him and says, "I didn't know you still needed one." Well, if you're British, we get that joke, because Australia was a penal colony. A lot of, it was a very efficient way of dealing with prisoners. What we did is we sent them to Australia, and they essentially they served their 10 years or whatever it was, their sentence, mostly not in jail. Do you know what they would do, because money was important? You would basically sell them to farmers as labourers, and they would have to work indentured for 10 years, or whatever the sentence was, and then at the end of that 10 years, they got their freedom, and most of them just stayed. They were free men, and they just continued to live. So that was part of Australia's background. It came from penal colony. It was caused by the fact that a lot of in that time in the British Empire, at least, they had to figure out ways of getting their population that they considered the undesirable parts of their population, let's phrase it that way, out of the country, because they had this image that if we can get rid of the riffraff, we'll be a better country for it. So criminals would be a definite riffraff, right? Who wants criminals, right? Nobody wants criminals. So they said, well, ship them off to Australia, they're gone. You know, we don't need to pay for anything. In fact, in Australia, you see the farmers who paid for the prisoners to work on their farm? They had to pay money to the Australian government, who then gave it back to Britain. So Britain was actually one of the few countries in the world where prisoners make you money rather than cost you money. So it was, in a lot of ways, it was a good idea. I need another joke. That was too short. Oh, this one is about sharks. You ready for sharks? Daddy shark and baby shark were off the coast of Australia, you know, great whites. And they saw this fishing boat and it was sinking. And then finally it went under the water and there was like 4 fishermen, didn't have time for a lifeboat in, and they were just, you know, treading water. And the little baby shark says, Dad, can we go and eat people? I want to eat people. I've never tried them. They taste good. And he starts to shoot off and his dad grabs him and says, no, you don't eat people that way. And the little baby shark says, what do you mean? He says, look, watch what I do. This is how you eat people in the water. So, you know, the shark music, which I can't do. And the shark goes towards the guys and then he pops his fin out and all the fishermen start screaming and get closer. And then he zooms in and then about 20 feet out, he circles them, with the fin coming even further out of the water. And this time the guys are panicking and screaming and shouting and thrashing and everything. And then he zooms in and eats them. And the little baby shark goes, at the end, goes to his dad and says, that was an awful lot of work. Why do you do that? Why don't we just go in and eat them? And the daddy shark says, well, you know, people taste better when you scare the poop out of them first.
That was good.
You like that one?
Yeah.
I can never figure out what you like as a class. Okay, you actually like the poop joke.
That was a little funny.
You kind of overestimate the intellectual abilities.
I
of this
definitely
group, I think.
kind of did there. So anything to do with peeing and pooping, you're in for it. Is that what you're saying?
Well, I mean, it is funny still.
Okay.
I may be 24, but I don't act like it.
So, and you shouldn't. I'm a great believer in you should never grow up. Life is much more fun when you stay young. Just miss. So have fun with things. Darn if I can find the page I'm looking for. I think it's here. Nope, it's not, but I can get it. It's here. Yay. Right. You can't see it, but I am getting to it. This is section 4.2. I'm putting a view up, and once it's up, I'll come back out, and then you can see it. We're going to look at some of the homework questions, because I'm sure there's bits I need to go into detail. Just in case, can you actually see 4.2 homework? I don't think you can, but just in case.
No, we cannot.
Okay, so it's out and in, and we'll have it any second now. Here we go. Right, so question 1. 2 events are independent. If the probability of A is 0.65, what's the probability of A given B? Actually, I just gave that as an example, something similar to that. Isn't the answer exactly the same probability? If you're independent, doesn't the probability of A given B is the same thing as just A, right? No effect. Suppose P of A is 0.3 and P of B is 0.5. If A and B are mutually exclusive, compute that. Right? Well, won't that just be add the 2 together and you're finished? Right? If you're mutually exclusive, don't you just add one or the other, right? You add them together. If PA plus B is 0.2, now compute it. Well, you would go 0.3 the first one. That's A. You do 0.5 the second one. And then wouldn't you subtract that guy? Oops. Now I'm just putting in the calculation. Do you see what I did there? It's A, probability of A, plus probability of B, take away the probability of both. That was one of the formulas that we got earlier. Oh, this one I didn't do, so this is going to be fun for me as well. Event A is the driver is under 25 years old, and event B is driver has received a speeding ticket. Okay. We have to figure out how you would write this sentence that's in English and transfer it into one of these fellas here. What's the probability that the driver has received a speeding ticket and is under 25 years? Which one of those 5 dots, which one of these 5 things represents that probability?
Be the last one there, wouldn't it?
Yeah. You know, it might have been easier if they said B and A, so they got the order right. But you know, A and B and A are the same thing, aren't they? You know, 1 and 2 is the same thing as saying 2 and 1, right? How about this one? The probability that the driver has not received a speeding ticket or is under 25 years. Well, let's start with a clue, and it's a very small clue, but it's a very easy clue to use. Doesn't this have an or between the two situations? Right, something or something. Do you see that? Doesn't that immediately mean it has to be this one or this one? Now, it's made up of 2 chunks. The first chunk is a driver has not received a speeding ticket. Isn't A, you have received one? So how do you write not received one?
B.
Right, we have a little C above it, right? Okay, I've done enough for that one. You can do it. 6 is the same basic idea with new calculations. Right, now, here we've got an empirical probability. It's down with colours and percentages, which is fine. I can handle that. Suppose you have a large bag of M&Ms and you choose one candy at random. Find the probability that it's a green candy or a blue candy. Now, in this case here, aren't all of these mutually exclusive? Orange M&Ms can't also be at the same time green M&Ms, right? So if you want to do an or in this case, wouldn't you just look at the greens, which is what, 6%? And what's the other one? Blue, which is what, 10%? And wouldn't the answer here be 16%? Now, if you write it as a decimal, it's that guy. And I am looking for a clue. Have I missed anything? Does it say whether they want decimal or they want percentage? Because I can't see it if they did. Which means it's their fault for making my life hard. Okay, I'm going to go with this. When in doubt, do decimals. Now, if it comes back and says wrong, I'll just go back and turn it into 16%. And do you know when you do your homework, it doesn't care if it's the first shot or the third shot. If it's right, you get the full point. So it's not like you lose a point for being wrong the first time. Now, it says, are these 2 events mutually exclusive? Well, I kind of answered that one, didn't I? Say no. But which one of the three no's is actually the correct description of that situation? Are they mutually exclusive?
Oh, yes, because it cannot be both.
Can't be both. Okay. This one is to do with numbers, and it's the same idea. Oh, we're rolling dice. I like rolling dice. If I got my guy, I do have my guy. Roll 2 dice. One is green, one is red. Okay, mine is blue and red. We'll pretend it was green and red. And are these outcomes in the dice independent? Oh. At least they tell me here to write the answer as a fraction, which was helpful. Okay, if you roll a green dice and then you roll a red dice, does the green dice have any effect on the outcome of the other colored dice?
No.
No. So don't we call that independent? So are they independent? Yes, they are. Right? They have no effect on each other. Now, find the probability of 5 on the green dice and 3 on the red. Well, if you go through my table, which I'm not going to show you because it'd be too much out and in, isn't there 36? Oops. Remember the guy. There we are. 36 of them, right? Isn't there only one situation where it's a 5 in the green and a 3 in a red? 1 out of 36 choices. Now, 3 on the green die and 5 on, is that not the same thing? Let's check. 5 on the green and 3 on the red, or 3 on the green and 5 on the red. There's only one out of that one. That one threw me for a loop. And the last one, oops. And the last one is find the probability that you get a 5 on the green dice, a 3 on the red dice, or a 3 on the green dice and a 5 on the red dice. God, they're making that weird English. How many ways can that entire horrible event happen? How many situations out of the 36 end up being what they just said there? Because I'm not going to rephrase that. They're making a meal of this question. Isn't there one version for the first thing and one version for the second thing? Five and 3, 3 and 5, right? 2 different things, 2 things out of 36, which you would probably, because it's a fraction, and they want the answer as fractions, you would call it 1/18. Here are some dice questions, quite a few of them. Here's a card question. I think I should do a card question. Yeah, let's do 14 then. You draw 2 cards from a standard deck of 52 without replacement, which is what you normally do. Are the outcomes on 2 cards independent? You take a card and then you take a second card. Are they independent of each other?
No, they're not, because you're removing one of the options from the pool.
Right, and wouldn't that, depends on what the option is, couldn't that at least have an effect on the other one? Suppose you were interested in kings. If the first one you turn up as a king, doesn't that mean there's less kings to get on your second card, for instance? So if they have an interaction where you know it's going to affect them, at least in some circumstances, then you know that that's going to be dependent of each other. Now, 10 on the first card and 3 on the second. Okay. How many 10s are there in a normal deck of 52?
4.
Right. So I'm not doing the whole thing. I'm just writing down what the calculation would be. Wouldn't that be 10 on the first card, right? And then I'm going to multiply that by the next card. Okay. The first card has to have been a 10, right? It's already used up. That's what the 10 on the first card is telling me. Aren't there only 51 cards left now? But how many of them are a 3?
4.
So in this case, do you see that the top number didn't change? Only the bottom number. Oops, only the bottom number. What would the difference be if it was a 10 on the first card and a 10 on the second card? What would be the only difference in that calculation if you had a 10 on the first card and then a 10 on the second card as well?
The numerator would also decrease by 1.
Now, I don't think they do this, but let's do it for fun. Suppose it was 3 cards and all of them have to be 10s. Would you agree that there's only 2 cards that are 10s now and there's 50 cards still in the deck? So you would go 2 divided by 51. And then one more time, times 1 card out of 50. Do you know the chances of being dealt 4 10s is like ridiculously small? It's like 1,000,000 to 1 kind of thing, right? And you know those cowboy movies where the guy gets 3 aces or something and he's all excited? Whoops. Right. I don't know, the movies I'm talking about, but the guy looks at his hand and he says 3 aces and he goes, wow. You know why you should be looking and going, wow? Because how unlikely that is. And in fact, 3 aces is the best 3 of any card you can get. So that would be a definite plus event. And they move on to this fella. And I'm going to be doing this one in a lot of detail, but you're going to have to wait a few seconds so that I can copy it down so we can look at what's going on here. So it's a very medical one, so I'm hoping that you have seen, you know, they've talked about this perhaps in some of your classes about why testing is important and how that no test is perfect. Some tests miss the cancer cells because it's like only got 2 cancer cells and you can't do it when you do a biopsy and you're looking for malformed cells, and if there's 2,000 cells in front of your face, isn't it easy to miss a cancer cell, right? Tests. But there are other tests where you take blood tests and you do whatever that might be, and then you come up with does this person have COVID or does this person not? Do you know those tests are not perfect either? Some people will get the test and there will be a thing called a false positive, and then there'll be other things called false negatives. And they are quite serious in the medical world because the world is not perfect. And so we have to figure out how to put numbers into this situation. So here is the data I just copied. So let's just say, I'm making this story up. Let's suppose this is a test for HIV. And this represents people who do have HIV condition present, and this is condition absent. So this is people who don't have it. And this test is positive, says that you got the test and the test came back, you've got HIV. And this is the test is negative, right? You tested negative. And this means that you got the test and the test says you do not have HIV. Now this was conducted on 200 people. So can we pretend this is way back in the beginning of testing for HIV? Because the earlier you can test and are successful in that test, can't your chances of improving and saving that person's life improve, right? it's much better to catch cancer in its very early stages. The success rate there is much higher than if you catch it at, you know, the later stages of that disease. Now, there is a ton of numbers here. Let's find this guy. Let's find the probability of what's called a false positive. What does a false positive mean in medicine? Well, it means that you tested positive for whatever the disease is, and we're pretending it's HIV, when in fact you didn't have HIV. So that would become the probability that you tested positive given the condition was absent. Do you see that that false positive is actually a conditional probability? Does that make sense? So we are going to calculate what that is. Now, if I tell you that given that your condition was absent, if I'm telling you that, doesn't the world now just belong here? So that means there are 69 people that they did this on. And how many of these people were actually tested as positive? And the answer was 24. So do you see where I got the numbers? 24 tested positive. You're told it's conditional, so there's 69. The world just basically consists of 24 over 69. Those are those are false positives. And I'm going to convert that into a percentage. And that's 24 divided by 69. And the answer we got there was about 35% of people had a false positive. Now, can you imagine what that was? You went to a doctor, he did the test, you wait a few days, and you get the dreaded phone call. And the dreaded phone call says, your test results are back. I'm sorry to say that you've tested positive for HIV. 35%. That is not good for your mental health, right? Because that's a pretty serious disease, right? I know it's much better treated now, but it used to be a death sentence at the beginning, didn't it? They really could reduce they could make you live longer, but they couldn't figure a way of, you know, eradicating. I believe now that they've found ways to essentially, if not eradicate it, at least get it to the point where you'll live just as long as if you didn't have it. Well, false positives are not good, right? 35% of people who don't have it are going to test positive for HIV. Let's look at the alternate, a false negative. Now, a false negative is a conditional probability as well. Isn't a false negative the probability that you tested negative given that the condition was present? Which is just another way of saying you've got HIV, but you took the test and the test says you were fine. That is not good news either. But now the world has changed. Since the condition is present, isn't that the only part of the world that matters? And how many of those people tested negative? 25 out of a total of 131. So that's going to be 25 out of 131. And I'm not looking too happy about this either. That's about 19%. So if this was in the early stages, and this was one of the many, you know, when something happens, what they do is the pharmaceutical companies all kind of try and find ways to test, right? In the COVID, right? It's not one company, there's probably 10 pharmaceutical companies, I mean that number up in the world, who are looking at testing, right? And sometimes you get a really good test really early on, but sometimes you get a bad test. And to me, this is a bad test. It's almost worth not having the test anyway. Do you know these people who think they're safe? Couldn't they continue with their activities in a way that would be dangerous to them and others because they think, I'm fine? That's a very serious one. This one you can live with, I guess. Being told that you've got something that you don't probably won't kill you, right? It'll make you really unhappy and it might stress you out for a while, but we would assume that they would have backup things, right? You'd come in and get a more detailed test, or you would, you know, they would look for other symptoms, and then they would say, yeah, it looks like that was just a false positive. Sorry about that. You know, there's 2 weeks of your life you're not getting back, but at least you're fine, right? So when you're looking at these two, do you know that there is a balance in the medical world? Here's a visual of it. If you have false positives and at the other side you have false negatives, do you know if you want to make one of them smaller, aren't you going to make the other one bigger? So if you can imagine you get a drug test and the drug ends up being, you know, some like 0 to 50, right? And you decide 45 or bigger, you've got the disease, 45 or less, you're healthy, right? You see, if you move that number around, won't you then increase your success rate on one, but automatically decrease your success rate in the other? Give you an example, very silly example. I could make an HIV test today, cost you nothing. Every single person that I test, I say you have HIV. Won't there be 0 false negatives? Won't I be 100% right for those people who've got HIV because I said you had it, right? Won't the other percentage be ridiculously big? Now, that's at the extreme. So if you go one extreme, you'll catch everybody. But if you catch everybody, won't you have a big problem with the fact that everybody gets caught and nothing? There is no information in that kind of test. So when you are doing a test, you know you're guaranteed to have false positives and false negatives, no matter where you decide the boundary number is. So guess what your decision should be? Shouldn't it be in risk management? I would err on the side of a few more people being identified as being ill who were okay, right? That's a false positive. I don't mind making that a little bit big if that gives me less people who test false negatives. Now, I can't go the 100% for the argument I gave a few moments ago, agreed? But I can tweak it a little bit. And then you have to look into what is very often the case isn't the testing just the beginning of the process? Okay, you've tested positive, come in next week, we're going to do a whole batch of other tests, we're going to check for this and that and so on, and then they can come across it. So it's like a way of sifting through the population so that you can identify the most likely candidates, and then you spend all your money and time. Because your doctor only has a finite number of time, right? And labs only have a finite amount, people who work there. So you can't test everybody for everything all the time. Right? I mean, it's just physically not possible. So you have to select. So that's a cool question. And anybody in the medical field heard or any details about false positives and false negatives? Is that something? Anybody want to share anything about that? I mean, what did they tell you? It's a bad thing, I suppose.
It's funny because the way physicians address it that I've run into is, they assume that everyone is aware of this, and so they don't even tell you like percentages. They just say, hey, sometimes it can be right, sometimes it can be wrong. Okay, have a nice day. I'll see you next week. And then that's kind of what you're left with. I think that's kind of funny.
Yeah, it would be nice. This data is empirical, right? This is not theoretical. Do you know this is just based on 200 people? Now, if you've got a big enough sample of people, you should be able to say, okay, you've tested positive, but by the way, 35% of people test positive. Would that make you feel a little bit better than, you might have it, you might not, we get it wrong sometimes? That's kind of hard to, I don't know what the word I'm looking for, hard to accept, isn't it? I mean, being a math person, if you can put numbers on things, at least I feel I know more. If you gave me, if there's a COVID test out there where 90% of them were false positives. Do you know that's a waste of good money and resources? Because those people who tested positive, aren't they going to change their lifestyle? They may even, end up being in hospital to get a checkup just to make sure that they're not going to catch anything more severe than that. So that was a cool thing. So we are reaching an interesting point. I'm going to continue, but your time is valuable. So what I'm going to be doing for the rest of this time period is I'm going to hang about, and you're going to stay behind if you want, and if you're not, you're going to go and start your homework and do what you like. And for those that stay behind, we're going to just go over some extra questions and give you some more practice. So that's kind of my goal. So to make it less obvious, you've got a 5-minute break, and if you don't come back, I'll know why. Okay? So I'll see you in 5 minutes, or I won't. Hi, Brianna, can you hear me? No. Kiara?
Yes, I can.
Cool. Are you going to be a stayer then?
No, I think I'm good on the homework. I think I'll be okay.
Okay. Courtney, you good? Stacy, are you good?
Yeah, I'm good.
So you going to hang around?
Yeah, mine as well.
Okay. I don't think I got an answer back from Brianna. Brianna, can you hear me? You may not be on audio, of course, so you're on chat. Okay, let me check that out. No, that was just someone saying bye-bye. Jenna, can you hear me? Don't know what's happened. She's went for a coffee and didn't come back. Nika, can you hear me? Yeah. Are you hanging around, Nika?
Yeah, I'm gonna stay. Thank you.
Okay. Who else have I not asked? Daniel, are you around? Still getting his coffee. Give me a few. Are you lot seeing WebAssign? Not quite sure what pictures you get to see. This is, what's that? That's a video link. We don't need that right now. That's my Calc 3. I don't need that. Guess we don't need that. Yeah. Hi, Jenna. Are you staying? Or not?
I guess so.
You can or you can't. Honestly, I have no problems either way. It's whatever suits you. Your time is valuable. I want to make sure you use it the way you want to. Okay?
Yeah, cool.
Right. Okay, let's get started. We got the first thing I think I'll show you before we get into doing some more homework questions. And essentially, I'm just going to load up the WebAssign and we'll go through some of those questions I skipped by. And if you've got any homework questions before that, maybe we should do them first, so we can, go over anything that's causing the issues. Where are we? Are you lot looking at our module our Canvas? Okay. Now, what you might notice here is that we have all the Zoom class lessons. Right? So if you find that maybe I didn't go over something as deeply as you wanted, or you want to see another insight into it, when I click on this, do you see this picture now? Or do I have to go out and in? Right, so I have two 146 classes. I have a daily class, which meets 4 times a week. And this is their lectures. That's why there's so many of them. Theirs are much smaller. But you can imagine, I did one this morning with them, but that won't be up until tomorrow, and that'll go here. And I also have put here our Zoom lesson. So when we're finished today, again, it probably won't happen till tomorrow. Our lesson 4 will go here. And so you can go back and watch some of the earlier videos from other classes in case you feel that you need some more details. So that's one of our resources. Kick up. Here's chapter 4, probability. This I don't know. Who knows with this thing? If I click on this, do you now see a whole load of little videos? Okay. You've probably been here before. Do you see videos on the multiplication rule, conditional probability, and some of the things that we've been doing today? So if you say, yeah, I think I'm okay, but I need to know that addition rule thing he was talking about, which is from mutually exclusive. I'd like to do that one. And so you could watch a little video and it gives you some more ideas. I find it helpful if you don't just do it the way I do it, right? But you actually see other people's way. And if you click down into PDF files, see this guy here? That's notes that I've made on probability. So there's some dice questions in there, some conditional probabilities, some stuff with independence. So really just giving you a kind of heads up that you should always go and look at Canvas. There's tons of stuff in Canvas, right, that you might not have noticed. When things become old, they just drop down into this bunch. So there's chapter 1 and 2 and 3. So when you're studying for your midterm and you want to maybe go over some stuff, you could go there and there's some resources for you. Cool. What else is there? I think that's it. Now, let's kick out of that. Let's look at conditional. I'm pretty sure I'll have to get out and in. Oh, is there anything, let's rewind a minute. Is there anything that you want me to go over before we start looking at chapter 4.1 and 4.2 homework in a little bit more detail? Any other earlier questions? Okay, so I guess I should probably start at 4.1 and then move on to 4.2 after that. I think we covered those. We did do that. Yeah, we did that. We did this one. Okay, I guess let's look at 7. I didn't do all of 7. Why is negative 0.41?
We can't see it.
Out and in. Right. I think it's this one. Yay. Okay. Why is negative 0.41 not possible as a probability? And you've only got 3 things to choose from.
Because it's not between 0 and 1.
Right. I would probably go for the obvious questions first before you talk yourself out of it, and that's the answer. Is it 1.21 not between 0 and 1? I wish they had a little bit more imagination. You know, things like it's bigger than 1. Wouldn't that also stop you being a probability? You know, if a probability is larger than 1, it's not possible. If a probability is less than 0, that's another way of saying negative, it's not possible. What about, can 0.56 be the probability of an event? So which of the yeses is the real reason?
Because it's between 0 and 1.
Correct. Why is between 0.5 and 1 not the better answer? Why is it the first one, the third, I guess, the third one, and not the fourth one? Could 0.4 be a probability? But it's not between 0.5 and 1. Do you see? If you want it to be true all the time, don't you have to pick the third explanation to be true all the time? And we did the wiggle the ears one. We talked about this one, but we didn't talk about this one, 10. I don't think we did anyway. If you roll a single dice and you count the number of dots on the top, couldn't they just say you rolled the dice and what did you get? Because that's what you do, don't you? Count the number of dots on the top. Seems more information than you need. What is the sample space? There are 4 choices there. Only one of them is correct. Which one is it? The top, the second, the third, or the fourth choice? You roll a dice and you want to know all the things that could happen. That's what sample space is.
The fourth choice.
What's the alternative if it wasn't the fourth one then? You agree it's the first one? There's only one difference between the two. Isn't the top one, the first one I'm calling the top one, 1, 2, 3, 4, 5, 6, and aren't they all equally likely? If you roll a dice, can't you get a 3 just as often as you get a 2? That's why it's the top one and not the last one. The last one says, yeah, the numbers are right. It is 1, 2, 3, 4, 5, 6, but they're saying they're not equally likely. Now, I know I'd like a 6 when I roll a dice, at least for most games I do, but isn't getting a 6 just as easy as getting a 1? Now, it then says assign probabilities to each of these. This is overkill because you're going to look at that and you're going to think, oh God, this is going to be hard. But isn't the answer 1/6 for every single one of them? What's the probability you roll a dice and get a 5? Isn't it 1/86, 1/6? Think easy before you start making life hard for yourself. Now, it says, do these probabilities add up to 1? Can you trust me if you did a whole load of 6s and there's 6 1/6ths, don't they add up to 1? Now, there was an earlier question where the answers were decimals, and in those cases, couldn't you sometimes get an answer that's either 1 or very close to 1? But rounding off might cause a little discrepancy. Okay, what's the probability of getting a number less than a 4? You roll a dice, you get less than a 4. Think simple.
1/2.
Yeah, 3/86, 1/2. What's the probability of getting a 4 or a 5? Isn't that 2/86, which becomes 1/3? There wasn't this is the simple probability one, so you got to remember that the answers are going to be in your face obvious to the point where you'll talk yourself out of it. Now, it can't be just every single one of them's a 6. No, it can't be that. Well, guess what? It is in that question. Now we're on to, I think we did the inventor one, so let's do a botanist one then. A botanist has developed a new hybrid cotton plant that can withstand insects better than other cotton plants. That's cool. However, there are some concerns that the germination of seeds from the new plant establish the probability that a seed from the new plant will germinate. A random sample of 3,000 seeds was planted in warm, moist soil, and of these, 2370 germinated. Use a relative frequency to estimate the probability that a seed will germinate. Now, after that entire couple of sentences, do you know the only thing I need to worry about is how many germinated, which is that number, right? And divided by how many seeds were planted, which is that number. And do they want it? Yeah, they want it as decimal. So I'm going to go 2370, and I'm going to divide it by 3000. And I'm getting the answer. Oh, come on. I had to do a double take here. You know, the way that question is phrased, shouldn't you get a really ugly decimal that you have to round off to 3 decimal places? Yet I ended up with an answer that worked really nicely. Go figure. Now, if that's the chance that it will germinate, I don't need to do a really big calculation to figure out what's the probability that it won't germinate. How come I know it's that?
It's a compliment.
Yeah. Remember, something happening, its opposite called its complement, that's a good word to use, is the rest. If something's 40, won't the other be 60? That kind of relationship. So if one's 71, won't the other be 21? Adds up to 100. What's either a seed germinates or it doesn't? What is the sample space in this problem? You only get 3 choices, so you have to figure out which one of those 3 they're expecting you to choose. What are all the things that could happen? Isn't
Germinate
it?
or not germinate?
That's it. End of story. If you roll a dice, isn't the sample space 1, 2, 3, 4, 5, 6? If you pick a card from a deck of 52 cards, technically isn't the sample space all those 52 cards? I'm not going to mention them by name, but that's what the sample space would be, right? If you throw a coin in the air, isn't the sample space heads or a tails, right? 2 things. Do the probabilities assigned to the sample space add up to 1? Yes, they do. Are the outcomes in this sample space equally likely? No, they're not. Isn't the chance that you germinate much bigger than the chances that you don't germinate? At least more than 3 times as likely. So I can imagine this new hybrid of cotton, right, the disease-resistant hybrid, that might not be a high enough germination rate to make it a successful crop. Because roughly, very roughly, won't 1/4 of the seeds that you sow die in the ground and never come out as a cotton plant? So you do a whole load of planting, right? And can you imagine right off the bat, 1/4 of your cotton plants never even become cotton plants? Couldn't that be quite a inefficient use of your cotton land? You would hope that you get a really high germination rate, so everything you plant turns into what you want. So that would worry me. That's just my question. Oh, the last one. Oh, okay, I'm going to write this one down and then we'll switch to it because there's so much going on here. 135 people. Walk to buy a store. Okay, that's a piece of information I'm going to use. 52 of them walked in. And of the 52 who walked in, 29 of them bought something. And I'm writing down the questions. Estimate the probability that a person who walks by the store will enter. So find the probability that they enter given that they walked by. Right, question B says estimate the probability that a person who walks into the store will buy something. So that now becomes the probability that you buy something given that you entered. C, what's the probability that a person who walks into the store will come in and buy something? I thought that was B. What's the probability that a person who walked into the store will buy something? Okay. What's the person who who walks by the store will come in and buy something? Ah, okay. So what's the probability that you buy something given that you walked by the store? Okay. And last but not least, the probability that a person comes into the store will buy nothing. Given that comes into the store. Okay, you'll get to see what I've written now. You have to be very precise in what each one of these stories is talking about. So, I think walked by is probably a bad phrase because doesn't that make you think they all walked by? But not all of them did. Didn't 52 of them walk in? Right. So the way I'm looking at that is maybe walk by is a bad choice. How about 135 people were outside his store at some time? And of those 135, 52 of them walked in, right? I guess they walked in and had a look about. And those 52 people, 29 of them bought something. So all the numbers that we're going to be answering these 4 questions come from here. The questions weren't phrased directly as conditional probabilities, but nonetheless, that's what they were. So for instance, what's the probability that you enter given that you walked by the store? Right. If you the people who walk by are 135, right? That number always goes in the bottom. Of that 135 people, how many of them entered, walked in?
52.
Right. You nailed it, both of you, 52 at the same time. Can you imagine, I'm not doing that, but can you imagine you turned that into a decimal and you'd be done, right? Okay, what's the probability that somebody bought something given that they'd entered the store? Well, if they entered the store, isn't that 52 people, right? They walked in. Of those 52 people, would you agree that 29 of them bought something? And that's the answer to that one. Have you noticed that the conditional, the thing you know has happened, always gives you the bottom number? And then you get the top number by looking at only these people and how many of them are that. Right, look at this one. What's the probability that you buy something given that you walked by the store? Now, if you walked by the store, wasn't that 135 people? Right. Of those 135 people, how many of them actually bought something? Isn't it still 29 people? I mean, they had to walk in, look around and buy something, but at the end of the day, didn't they buy something? Right, last one. Buy nothing, given that they came into the store. Okay, what's the bottom number on this last probability going to be based on what I've said before? How many people is that, the condition? How many came into the store? They've phrased it different ways, but how many people did that end up being?
52.
Agreed. Now this one is really sneaky. How many people bought nothing? Now you got to say from what subgroup? Only from the people who came in, right? Only from those 52 do you figure out the ones who didn't buy something. So if you look at this 52 and you take that number away from it, isn't that how many people didn't buy something? And if you take 29 away from that, I believe it's 23. And that would be your answer to that question. Are we good? If there's nothing else that you've noticed that you've been maybe scanning through from 1, can we move on to 2 then? Okay. So, let's see what we have. And I'm going to have to do a whole load of closing and opening and all that good stuff. Okay. This is the second time Zoom's done that. Okay, I'm a little bit lost here. I'm good. Okay. I've closed and opened so many windows, I don't know where I am. But now I think I know where I am. Right. Can you hear me, guys? My Zoom just went away and came back. Rihanna, can you hear me? Rihanna, I can't hear you. Okay, we got thumbs up. We'll go for it. Where the heck happened there? Right, let's try it. Third time lucky. Are we looking at homework and nothing has crashed? Right, let's go for it. We did that one. We did that one. Okay. Don't think we did 3. So let's look at 3. We're told that the probability of A happening is 0.4 and the probability of B happening is 0.6. If the two events are independent of each other, how do you find the probability of A and B? Now, and is not the same as or. When you see the word and, shouldn't you be multiplying two things together? Great. So, if they are independent, won't the probability, I'll write this down and I'll come back out, I think. This is 0.4 and this is 0.6. Okay, so I'm going to leave that. I'm going to stop this guy. I'm going to go into my little picture. Here we go. Now, I'm trying to see if I can find my piece of paper with the formulas written down on it so I don't have to rewrite it. It's a bit of a mess, so I'll put it over here. If two events are independent and you want to find the probability of A and B, then the answer will just be the probability of A times the probability of B, in which case it's going to be 0.4 multiplied by 0.6, and that gets you 0.24. That is allowed because A and B are independent. So far, so good. Now, can you remember this guy? we're being asked to find this. Oh, I believe they told me this guy was 0.2. So we're being asked to compute A and B given this information here. So we need to figure out which of the various formulas we've got. So I am going to be finding the probability of A and B. And I'm going to use the probability of A given B times the probability of B. So essentially, I'm using this row here, right? This third formula. Now this guy is 0.2 and this guy is 0.6. And that gives me the answer 0.12. So do you see in this second situation here, the answer is not the same as this one. Right? A and B when they're independent is 24% of the time. A and B when you're told this is only 12% of the time. If you are given a value for A given B and it is a number that's not the same as this number, it means that A and B are not independent. It means that there are some overlap, some connection that maybe make it more likely or less likely for what you want to happen. In this particular case, it ends up being less likely, right? But you can imagine what that might look like. So if you know that the probability of A given B is the same thing as the probability of A, can't you use that as a test of independence? If A and B are independent, this will be true. If A and B are dependent, that's just a fancy word for not being independent. If A and B are dependent, that's not true. So I should do a quick check on that. If this guy is 0.2 and this guy is 0.4, doesn't that mean they're not independent? Right? They're not equal to each other. Are we cool with that? Any questions? Right. Let's stop here, go back out and back in. And I think we went through one version of this. Let's look at the other version that's similar. Let's look at question 6. Okay, so consider the following two events. A, the student is female, and B, she's majoring in business. Right? No, not she. B, any student is majoring in business, right? There is no necessarily connection here. Translate each of the following. So what's the probability that a student is male or is majoring in business? Well, I'm going to look at the key word here I'm looking at here is or. And when I look at or, I don't really have many choices, do I? But let's continue. If you're a male, doesn't that mean you're not a female? So isn't that AC? Are you majoring in business? Yes. So there's your answer. Suppose I had said to you, what's the probability that the student is male and they're not majoring in business? So they're a male or they're not majoring in business. Wouldn't that be AC or BC? Right. Now, question C is a conditional probability. Doesn't look like it the way I've phrased it, but it is. What's the probability that a business major is female? When they phrase it that way, doesn't that make you a business major? It's a given piece of information. That means I'm looking at conditional probabilities, and we're looking at given B. What's the chance that you're a female? A is a female. So aren't you looking for that one? The probability that you're a female given that you're a business major. That's how that would be expressed in the probability way. E, the probability that the student is female and is majoring in business. Right, I can see an and here. So shouldn't I be focusing only on this one or this one because it has the word and in it? Do you see that in probability, a little word like and the other word or actually is a big clue to what the probability should be? Things with and in them, don't they end up being probabilities with and in them? And things that have or, same kind of thing. So who we got here? She's female. If you're female, is that A or AC? Is event A female or is event A, is being a female event A, is being a female event AC? Which is it?
A.
A. Okay. Majoring in business. What does majoring in business look like?
E.
Okay, so why can't I see the guy I'm looking for?
Oh, I think it's
Oh, because the word I'm looking for is and I can't see it. I just, bad eyesight. There it is. Right? A and B.
Can you explain on the last one when it said, I can't remember what the line is called, given that.
Yeah, it's called given.
And that the difference between and in that situation, because that's not super clear to me for some reason, that it says a business major is female. I would want to say A and B, even though it doesn't say and.
No, it doesn't say the word and I can understand why you might think that, because in the English language, we may phrase something that way and people will know what you're talking about. But in the probability world, we every word is a prisoner, right? Every word has a meaning. So the way I would read this is, the first part of the sentence says, a business major. So what's the probability that you've got a business major? To me, that means, oh, you already know that it's a business major. And if I already know something, that means it's one of those vertical lines given you're a business major, right? Given you're B. Now, if you wanted to make that a truly and sentence, you would have to say a little bit differently. What's the probability that a person is a business major and is female? You would actually physically need to put the word and in the sentence to make it an and question as far as probability is concerned. So do you see that word and isn't a superficial just to make the grammar right? You see the and is actually vital to the question, right? If I said to you, she's a business major or a female, and I said a business major and a female, do you see those two give you a totally different answer? Right? So if you give me a few minutes, I'm going to set up some sentences like that and we can see if we can figure out what each would look like, right? So I'm going to just pick my own. You just have to kind of patiently. Okay, I've got some combinations here. And let's see if we can do some more practice at looking at these things from the way it would be written as a probability. So here's my story. There are two events. A, I don't even need to put the word is. A is your mail. B, you play chess, right? They're two distinct events. There may be overlap on them, there may not, but that's not what we're interested in right now. We're interested in these probabilities and how you would write them down. So the first one is, what's the probability or the person is female and plays chess? So, what out of that entire, 6 words is the key word to continue with?
And
So what's the probability someone is a female and plays chess? Well, isn't a female going to be that? And isn't plays chess going to be that? Okay, next one. What's the probability a male plays chess? Do you see in that sentence there is no and there is no or? So I kind of know it's not going to be those combinations. Are you told something? Do you know for sure if it's a male or a female, the way this sentence was written? You know for sure that they're a male, agreed? And that makes it a conditional probability. And a male is A, so you know it's going to be probability something given A. Now, what do you know about this male? They play chess. Third one, a male does not play chess. Well, very similar to this question, right? You know they're a male, but doesn't play chess. The complement of playing is not playing, right? What about this? A chess player is male. Okay. There's no and or again, agreed? It's not chess player and is male, chess player or is male, right? There's no and or in these sentences. Do you know something for sure here? What do you know about this particular person that's being described here? Aren't they a chess player? And since you know they're a chess player, isn't that given B? Given the thing you're told that you know. Now, what do you want to know about them? They are male. So that's the probability of A given B. Now, this last one has got an or in it. And when it's got an or in it, don't we have an or in the middle? And either side of that or, aren't we going to put A's and A, C's and B's and C's, right? The complements of the thing. Plays chess is B. And how are we going to write female? A is male. How are we going to write female? Agreed. A, B, C in it. Does it help if you see enough examples of and and or tell you and and or in the answer? No and or is going to lead us to some kind of conditional probability. So you read it. There might only be 5 words in the thing. So every word's a prisoner, right? Every word is there for a reason. So you look at it and say, okay, what do I know for sure? Oh, it's a male who plays chess. Oh, I know you're a male then, right? It's a chess player who's female. Oh, I know you're a chess player, right?
Yeah,
You know,
it's
and
like learning a new language. It's interesting. Like, it's actually kind of cool.
Yeah, it's you have to take the essence of what's there and crunch it down to just that. And because you have to do that, you see, it's a very, yeah, it is a language. Mathematics is sometimes considered a language, isn't it? It's a way to communicate information, in this case, in a way that's very symbolic. But it's still a language. We can transfer it into English, or at least partially. Are we good? Right. So I'll do my out and in thing again. You're hanging in really well. I wish I was as young as you and could do that for as long as you could do it, but I'm not. We did an M&M one, so let's do question 8. A national park is famous for its beautiful desert landscapes and its many natural rock formations. The following table is based on this information gathered by a park ranger on all rock formations of at least 3 feet. Ah, okay. Do you know, I'm getting at this. It doesn't matter for the question, but I just visualize it. Do you know you got those little rocks that are on top of mountains and are like 12 feet tall, and there's a little, it almost looks like it's a pebble left at the bottom and they're ready to fall over. You know, I think that's the kind of rock formations they're talking about. You know, like some of them look like statues and some of them get special names because if you look at them the right way, they look like a wolf, you know, the kind of weird rocks. So I think that's kind of what's going on here. And what you can see here is in the range 3 to 9 feet, there's 110 rock formations in that size. That's how tall they are. And there's even a couple of beauties. You know, a 75-foot or higher rock formation is a big honking chunk of rock, right? So for this, suppose you chose at random from this information, what's the probability that you get a height between 3 and 9 feet? The question is actually pretty easy to do. Isn't it 110 of them divided by the total number of rocks? And did they tell you somewhere what the total is? Because if they don't, I'm going to have to add the whole damn thing up. Okay, add them up. 204, 227, 227, 257, 261, 270. Now, I'm actually writing the answer down as a fraction, but bear in mind what they tell you. Soon I convert that into a decimal. So I would do 110 divided by 270. And 0.407 roughly. And can you imagine I did this guy and this guy and this guy and this guy? Wouldn't it be pretty much the same process? We go with that question. It's pretty much what you see is what you get. We've done that. No, you've got my dice things to do. I guess I should pick one dice. Let's pick 12. You roll 2 dice. Okay, I'll try to find my dice picture again. And what do you get? What's the probability of getting a sum of 7? Next one, what's the probability of getting a sum of 11? And the last one, what is the probability of getting a sum of 7 or 12? So 7 or 11, I should say. All right, that's the one I'll do. Okay, where are you going? There you go. Here's the guy I prepared earlier. Do you know you might want to get a copy of this, as I said earlier, print one out or something so you can work on it. Right, so what's the probability you get a total of 7? There are 36 things here, and if you add them all up, we already got that answer. It's that fella. What's the probability of getting an 11? Well, do you see it's only 2, these two? So what's that? 2 out of 36, which is 1 out of 18. Oh, I did that one as well. So what's the probability that you get a 7 or an 11? Now, and involves multiplying, or it involves adding and subtraction. Are these two things mutually exclusive. If it adds up to 7, can it add up to 11? No, right? They're mutually exclusive. Which means, don't you simply just add the 2 together? And that's going to get you this guy plus this guy over that guy, and then off you go. I think my brain is pretty much sponged by now. I'm not sure how much good I'm doing. So just for my own mental health, because I have a long day tomorrow, we'll round it off at this point. Is there any last minute questions that you want to go over? Something that is bugging you? Well done for hanging in so long.
Thank you so much.
You are welcome.
I really appreciate it.
If there's any questions that you might want to just ask on your own, because you don't want to ask with people, you just hang about for a few more minutes and I will answer them. Otherwise, bye-bye, guys. Bye-bye, Daniel, Janet. Brianna, I don't know if you went for a coffee and never came back, but you're still here, evidently. You bye, Nika? Is that you going? Okay, bye-bye. I'm out of here.